The black hole at the center of our galaxy is starving. Not metaphorically, literally, measurably, in ways that contradict everything standard physics predicts for an object this size. Sagittarius A-star has a mass 4 million times that of the Sun. We know this not from theory, but from 4 decades of direct observation, tracking individual stars as they orbit something invisible at the galaxy's core. Reinhard Genzel was at the telescope at the Very Large Telescope Array in Chile in 1992, looking at infrared light from the galactic center through a gap in the dust, when he noticed that faint points of light near the core were moving, not drifting, moving, fast enough that year-to-year comparison showed measurable displacement. He started mapping orbits. Genzel and Ghez, that same year, pointed the Keck Observatory's 10-meter mirror at the same region from Hawaii and saw the same thing. 2 telescopes, 2 continents, one invisible object pulling stars around it at speeds that required 4 million solar masses concentrated in a region smaller than our solar system. Both programs ran for over 20 years. Both teams published results independently. Both arrived at the same number, to within a fraction of a percent. In 2022, the Event Horizon Telescope produced a direct image of its shadow. A ring of light bent around a point of no return, 27,000 light-years from Earth. The object is real. Its mass is settled. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for the orbital work alone. The measurement was that clean. And the object they measured is almost completely silent. A black hole of this mass, sitting at the center of a galaxy dense with gas and dust, should be one of the brightest objects in the sky. Not in visible light, in X-rays, in radio waves, in the full spectrum of high-energy emission that a feeding black hole produces. The theoretical prediction is not vague. Given the amount of material available in the galactic center, Sagittarius A-star should be emitting energy at a rate equivalent to tens of millions of suns burning simultaneously, continuously, across the electromagnetic spectrum. That is not a rough estimate. That is what the equations produce when you put in the measured mass and the measured density of surrounding gas. Its actual luminosity is lower than that prediction by a factor of approximately 1 billion. Not 10, not 100, 1 billion. That number is the subject of this video. To understand why 1 billion is a problem, you need to know what a feeding black hole is supposed to look like. Gas and dust falling toward a black hole do not fall straight in. Stand at the edge of a bathtub drain and pour water from an angle. It spirals. Infalling matter does the same thing, and that spiral forms a disk. The disk is not static. Different parts of it orbit at different speeds. The inner edge moves faster than the outer edge, as anything in a gravitational well must. That speed differential creates friction between adjacent layers. Friction generates heat. And in the inner regions of an accretion disk around a massive black hole, that heat reaches temperatures of millions of degrees. At those temperatures, matter does not just sit there, it radiates. It converts gravitational potential energy, the energy of falling, into photons, and it sends those photons out into the universe. This is why quasars outshine entire galaxies. A single quasar, which is simply a supermassive black hole accreting efficiently at the center of a distant galaxy, can emit more energy than 100 billion stars combined. The energy source is not nuclear fusion, it is gravity. Infalling gas releasing gravitational energy as radiation is, per unit mass, one of the most efficient energy conversion processes in nature, more efficient than anything that happens inside a star. Nikolai Shakura was working at Sternberg Astronomical Institute in Moscow in 1972 when he and Rashid Sunyaev sat down with the problem of why X-ray binary systems, stellar mass black holes feeding from companion stars, produced the spectra they did. Shakura was in his mid-20s. The model they published in 1973 described a geometrically thin, optically thick disk where viscosity between layers drives mass inward and energy outward as radiation. It worked. It explained the X-ray spectra of compact binaries. It explained scaled up by many orders of magnitude the luminosity of active galactic nuclei and quasars. The thin disk model became the standard framework for accretion physics across 15 orders of magnitude in black hole mass. There is a theoretical ceiling on how bright an accreting object can get, the point at which outward radiation pressure balances inward gravity. This limit, named for the British astrophysicist Arthur Eddington, who derived it in the 1920s, sets the maximum luminosity for a given mass. For 4 million solar masses, the Eddington luminosity is a specific, calculable number. Sagittarius A-star is not near that ceiling. It is not near 1/10 of that ceiling. It is not near 1,000th of it. The factor of 1 billion shortfall is measured against a much more modest prediction, not the theoretical maximum, but the rate expected from the density of gas actually observed in the galactic center. The model says there should be light. There is almost none. A factor of 1 billion is not a rounding error. It is not instrumental noise. It is not a systematic uncertainty in the distance measurement or an artifact of dust obscuring the signal. The galactic center has been observed by the Chandra X-ray Observatory in orbit above the atmosphere, by the Very Large Array Radio Telescope in the high desert of New Mexico, by the sub-millimeter array in Hawaii, by infrared observatories operating at wavelengths that penetrate the dust clouds between us and the core. Every instrument, every wavelength, every independent team, they all arrive at the same conclusion. Sagittarius A-star is emitting 1,000 million times less energy than its mass and environment predict. I've spent time with these numbers, and I'm not sure I've fully absorbed what they mean. Not because the discrepancy is large. In astrophysics, large numbers are routine. It's that the gap sits between two things we're confident about independently. How much gas is available near the black hole, measured directly from stellar wind observations, and how bright the object actually is, measured across multiple wavelengths by multiple instruments. Both measurements are solid. The gap between them is not an observational artifact. It is a property of the system itself. The comparison sharpens the point. Active galactic nuclei, galaxies where the central black hole is feeding efficiently, are visible across billions of light years. Some of them were bright enough, seen from Earth, that early astronomers cataloged them as stars before anyone understood what they were. The quasar designated 3C273, discovered in 1963 by Martin Schmidt at the Palomar Observatory in California, sits nearly 2.5 billion light-years away and is still, on a dark night, detectable with a moderately large amateur telescope. It is 400 times the mass of Sagittarius A-star, but mass alone does not explain the difference. Sagittarius A-star, placed at the center of a galaxy with active accretion, would be one of the brightest persistent sources in the sky from Earth even at 27,000 light-years. Instead, it requires the most sensitive space-based X-ray telescope ever built to detect it in quiescence at all. Same physics, completely different behavior. Ramesh Narayan was looking at a printout of Sagittarius A-star's radio spectrum in his office at the Harvard-Smithsonian Center for Astrophysics in 1994. The curve was wrong for a thin disk, wrong in a specific way, too flat at high frequencies, too bright at low frequencies, inconsistent with the thermal emission a thin disk should produce. He had been looking at this curve and others like it from underluminous galactic nuclei for some time. That afternoon, the shape of the spectrum pointed him toward a physical regime that the thin disk model simply did not cover. His proposal was called an advection-dominated accretion flow. The name is technical, but the concept is precise. Under certain conditions, specifically when the accretion rate drops far below the Eddington limit, the infouling gas does not form a thin, cool, radiatively efficient disk. Instead, it becomes hot, diffuse, and geometrically thick. Picture a puffed-up torus rather than a flat disk, gas that has been heated to billions of degrees by compression and viscosity, but is so dilute that it cannot radiate that heat efficiently. In the thin disk, particles collide frequently enough to thermalize, to share energy, and to emit it as radiation. In the advection-dominated regime, the gas is too hot and too diffuse for efficient thermalization. The energy stays in the gas, and as the gas falls inward, it carries that energy, advects it, across the event horizon. The energy goes in. It does not come out as light. This is not a patch on the thin disk model. It is a different physical regime with different governing equations, different density profiles, different temperature structures, and different observational signatures. The radio emission from an advection-dominated flow has a specific spectral shape, that flat to inverted spectrum Narayan was looking at. The X-ray emission is suppressed relative to a thin disk because the gas never reaches the temperatures that produce efficient X-ray radiation. The predicted luminosity for a given accretion rate and black hole mass is orders of magnitude below the thin disk prediction. For Sagittarius A-star, it fits. The quiescent radio spectrum, the suppressed X-ray emission, the absence of the thermal ultraviolet peak that thin disks produce, the advection-dominated model accounts for all of them, approximately. That word, approximately, is doing significant work in that sentence. It will matter later. Sagittarius A-star is not entirely quiet. Several times per day, it flares. A team at the Chandra X-ray Observatory was running a long monitoring observation of the galactic center in the fall of 2001, one of the first deep exposures of the region at X-ray wavelengths from orbit, when the count rate from the central source spiked. The instrument had been recording baseline emission for hours. Then, within minutes, the signal increased by a factor of several dozen. The flare lasted roughly 3 hours. It faded back to the quiescent level and did not return during that observation. The team spent weeks checking for instrumental artifacts, satellite attitude errors, contamination from nearby sources. The event was real. Even at peak brightness, Sagittarius A-star was still thousands of times dimmer than standard accretion models predicted for its quiescent state, but it was unmistakably there and unmistakably variable. Genzel and Ghez was at the Keck Observatory in 2003, running a routine monitoring session of the S-star positions in the near-infrared. The adaptive optics system was correcting for atmospheric turbulence in real time, producing images sharp enough to track individual stars within a fraction of a light-year of the black hole. At some point during the session, the central source, Sagittarius A-star itself, detected in infrared at last after years of trying, brightened by a factor of several within a single observation window. Ghez and her team watched it rise and fall within less than an hour. It was the first confirmed infrared flare from the galactic center. Since then, thousands of flares have been recorded at both X-ray and infrared wavelengths. They occur roughly daily. They last minutes to hours. Their amplitude varies. Some are barely detectable above the noise. Others reach luminosities tens of times the quiescent level. At peak, Sagittarius A-star briefly becomes the brightest X-ray source in the galactic center region before subsiding back into near silence. The most favored mechanism involves magnetic field lines. Gas orbiting near the event horizon carries magnetic fields, and those fields can become tangled. When field lines of opposite polarity are brought into contact, by turbulence in the accretion flow, by orbital shear, they reconnect. The reconnection releases stored magnetic energy as particle acceleration and radiation on timescales consistent with what Chandra and the Keck Observatory observe. It is the same fundamental process that produces solar flares on the surface of the Sun, scaled up by many orders of magnitude. The machine is not off. It is almost off. And the difference between those two states, between the flaring and the silence, is precisely where the physics becomes unclear. The other black hole we have imaged directly sits at the center of the Messier 87 galaxy, 65 million light-years away. The Event Horizon Telescope published its image in 2019. A bright asymmetric ring, one side hotter than the other, due to relativistic beaming as gas moves toward us on one side and away on the other. Messier 87's central black hole masses 6.5 billion solar masses, 1,500 times more massive than Sagittarius A-star, and from its core extends a jet, a collimated stream of plasma moving at close to the speed of light, stretching thousands of light years into intergalactic space, detectable in radio wavelengths, first photographed in 1918 by Heber Curtis at the Lick Observatory in California, who noted a curious straight ray extending from the galaxy's nucleus without understanding what he was seeing. That jet is the signature of efficient accretion. The energy required to launch and sustain it over thousands of light years comes from the conversion of infalling gas into radiation and kinetic energy at high efficiency. Messier 87's black hole is doing what the Shakura-Sunyaev model predicts for an actively accreting system. It is converting the gravitational energy of infalling matter into outgoing energy at rates that reshape the environment of an entire galaxy. Sagittarius A-star has no detected jet at comparable scales. It has flares that last hours. It has a quiescent luminosity 1 billion times below prediction. It sits at the center of a galaxy with far less active star formation than galaxies hosting luminous active nuclei. But the galactic center is not empty. The stars are there. The gas is there. The black hole is there. What is missing is the conversion. The silence of Sagittarius A-star is, I think, the most structurally important observational fact in high-energy astrophysics right now. Not because it is alarming, because a black hole that violates the dominant accretion model by 9 orders of magnitude, 27,000 light-years away, resolvable at the scale of individual stellar orbits, is the best empirical constraint we have on the physics of low-luminosity accretion, and we do not yet have a theory that accounts for all of its properties simultaneously. The galactic center is not starved of raw material. The stars within a few light-years of Sagittarius A-star are massive, young, and burning hot. They shed gas through stellar winds, continuous outflows of ionized material moving at hundreds of kilometers per second. Astronomers using the Very Large Telescope have tracked the infrared emission from these stars for years, measuring their wind velocities and mass loss rates, calculating how much material enters the gravitational sphere of influence of the black hole each year. The numbers are not negligible. There is gas. It is falling inward. The question is what happens to it before it reaches the event horizon. The answer appears to be, most of it never gets there. The gas being supplied by stellar winds is hot, heated by the winds themselves, by shocks where wind streams from different stars collide, by X-ray radiation from the galactic center region. Hot gas has high thermal pressure. High thermal pressure means the gas resists compression. An advection-dominated flow requires matter to actually reach the vicinity of the black hole. If the gas is heated past the point where gravity can hold it, it escapes rather than accreting. Observations at multiple wavelengths suggest that the actual accretion rate at the event horizon is orders of magnitude lower than the rate at which material enters the gravitational influence zone. Most of the gas is not falling in. It is circulating, being reheated, and eventually escaping as an outflow. This creates a layered problem. The thin disk model does not apply because the accretion rate is too low. The advection-dominated model explains the quiescent emission approximately, but does not explain why the system does not transition to a higher accretion rate when the gas supply is clearly present. And the magnetic field structure, which determines how efficiently angular momentum is transported outward, which determines how fast gas can spiral inward, is not directly observable at the relevant scales, even with the resolution the Event Horizon Telescope achieved in 2022. The stellar winds bring material to the door. The door barely opens. We do not have a consensus on what is holding it nearly shut, whether it is the thermodynamics of the gas, the geometry of the magnetic field, the angular momentum distribution of the infalling material, or some combination of all three that produces the specific regime Sagittarius A-star occupies. 4 million solar masses, 27,000 light-years, surrounded by gas, operating at 1/1,000,000th of predicted capacity, flaring briefly, several times a day, and returning to near silence. The advection-dominated accretion flow model fits the quiescent radio and X-ray spectrum approximately. It does not account for the flare behavior within a single consistent framework. It does not explain why the system does not transition to a higher efficiency accretion state given the available fuel. And no current model accounts for all three properties: the quiescent luminosity, the flare characteristics, and the suppressed accretion efficiency simultaneously with a single set of physical assumptions. The black hole at the center of the galaxy is 4 million times the mass of the Sun, surrounded by gas and barely eating. And we do not know why.